Hello. Today we're going to talk about Topic 4, Section 12, Collecting and Analyzing Data. So this section is all about how to design a survey or questionnaire effectively. Okay? So what I mean by that is, well, let's do it with an example. So, Zay is a student at an international school in Thailand. He would like to determine the average amount of money that an average Thai person spends each month on entertainment. So he makes a questionnaire, and he asks every 10th person that walks out of Starbucks at a mall near his home. So what's wrong with this? Okay, so how do we know we designed, or that Zay designed a good questionnaire? Right? What's wrong with his system? Well, he chose people at Starbucks. Well, that's not probably representative of Thai people. Okay? That is a specific age group or earnings class, right? You're not going to see many low-income people going into Starbucks. It's kind of expensive. Not kind of, it is. Coffee is expensive. All right. Also, he asked at a mall. Okay. People at malls tend to spend more money. So maybe asking them about what they spend on entertainment, well, you're probably going to get a biased result. Okay. And that's what we're talking about here. Great. So we know what's wrong with it. How do we fix it? Okay. So what can we tell them to do to remove the bias? All right. Well, what we can do is we could ask people coming out of grocery stores. Everybody's got to eat, right? And we could ask lots of people from different places around town. Okay. So the idea is we're trying to represent the entire population, okay, within our sample. So we don't want to only get the Publixes. I would get different grocery stores from all different parts of town. Okay, so it is super duper important that your questions are very well written. Okay? When you do personal questions, be very, very careful. Okay? Because people don't like to give out their personal information. So make sure you explain why. Okay, if I understand why you need that information, I'm more likely to give you accurate results. Okay, you want to encourage people to answer truthfully. Like, for instance, you don't want to ask a person's weight. All right, because there's a stigma on people's weight, so people tend to lie. So you have to talk about ways to get accurate results. Okay. All right. Precise questioning. Okay. You can't be vague or ambiguous. Okay. Don't be, how are you feeling? Okay. You can get a whole bunch of different responses with that. Okay. You got to make sure you narrow it down, and it's not, it's something that anybody can understand. You don't want to use these, highfalutin words that people don't understand. Structured questions are ones that, think of it like multiple choice. Okay, like I give you the possible answers. So that would be like, from on a scale, strongly agree to strongly disagree. From the list, pick your favorite water activity, that kind of thing. Now, it's really important to make sure that you've listed everything, all right? You don't want to say what's your favorite water activity and then not have surfing as an option, because that's kind of a big one. Let's see. You also want to be wary of the option other, because you might be leaving something out, or really it can be overused, okay? People tend, they don't want to pick one, or they're not 100% sure, so they just say other. Okay, so just be careful. Okay, so once you've decided on the design of your questionnaire, you have to consider whether it's reliable and valid. Okay, so first let's talk about reliability. This is basically how, if I were to do this trial again, would I get these results? Okay. How likely are my results to happen over and over again? Okay. So how can we know if our questionnaire is reliable? Well, we can do two things. We can either test, retest, which is we distribute the same thing to the same group of participants at 2 different times. Okay, and then we compare the results. Okay, so it's the same subjects just at different times. All right, but maybe that won't work with your data. Maybe you can only ask participants once. So another option would be to do parallel forms. So you create 2 different surveys or questionnaires designed to measure the same variable. So you give both of them to your same group, and then you compare your results. Okay, so instead of doing it at 2 different times, okay, you're giving them 2 different tests at the same time. Okay, because it's hard to get one person in there to take a questionnaire survey. It's certainly going to be difficult to get them in there multiple times. Okay, now you don't need to know exactly how to do or how to quantify this, but you do need to know how these are used. Okay. Now let's talk about validity. All right, so this is to determine whether our distribution matches the population. Okay, so does our sample, can it match the population? So 2 ways to test it. Criterion-related validity. Okay, if it accurately predicts the outcome for another measure. So like the SAT has criterion-related validity on affecting students' performance at college. Okay, it accurately predicts. So this is something that happens over time. Okay, because you'll see if the results are true. Another way to test validity is content validity. You have to determine if you're testing what you actually want to test. Okay, so your history teacher gives you your test in Spanish instead of English. Okay, but the teacher talks to you in English. All right, your textbook is in English, but now your test is in Spanish. So now it's really, how well do you know Spanish? Okay, because we've been talking about history, so you may not know Spanish or know very little. Okay, so that's how you would get, or that's how you measure content validity, right? Are you measuring what you really want to measure? Okay, so in the last section, we did 1-way contingency tables for chi-squared goodness of fit, 2-way contingency table for chi-squared test for independence. Now, we usually use them for chi-squared for categorical data, but we can with numerical if we split it up into intervals or categories. Okay, so take a second, read this example. Okay, it's talking about SAT scores and graduation, income after graduation. Okay, so salaries. So Cameron's got to decide how to split the SAT scores and the salaries to use chi-square test for independence. There is no set procedure for doing this. Okay, you can divide your intervals any way you see fit, as long as you can justify it. So Cameron split it up in this way, okay, which, it makes sense for the SAT because it usually jumps in 100 increments. For income, usually you jump into brackets from 10 grand, so that makes sense. All right, that also gives, small number of categories. You don't want to have 40 lists down here, okay? So let's determine if this is adequate. Okay, so Cameron needs to determine all the expected frequencies. They need to be greater than or equal to 5. That's known as the expected counts condition. Okay, so here we do the expected counts for each one. So we do the total, so 1 times 6 over the absolute total, and that gets that top one, right? 16 times 6 divided by 100 is 0.96, right? So these are the expected frequencies. So notice that we have a lot that are in bold because they are less than the number 5. And that's a problem. So based on the expected frequencies count, we must adjust the intervals. Okay? So we have to adjust the intervals. It doesn't matter if my actual data is less than 5. So these 0s, 2, 3, 1, those numbers don't matter. It's my expected frequencies. Okay, so Cameron was eventually able to make it into 2 columns and 3 rows, which is great. However, you may end up with only 2 columns and 2 rows, which is how many degrees of freedom? All right, when we have a two-way contingency table, right? Row minus 1, column minus 1, right? So if we have 2 rows and 2 columns, we get 1 times 1, so we get 1 degree of freedom. Okay, we don't really like that, all right, because that is a binomial, discrete binomial variables, or down to a binomial distribution, and we don't want to do that. Okay, it's continuous. So we have to adjust for this. To adjust, we use the Yates continuity correction. So we use this when we only have 1 degree of freedom. We adjust for it by subtracting all those differences by 0.5. Okay. All right, as always, an example's easier to explain. So here we have a questionnaire about eating breakfast and your gender. So we're going to calculate the chi-squared. So we have our observed contingency table. So that means we need our totals. Okay, so we're going to add in our totals. Then create the expected contingency table. All right, we multiply the n's. So 17 times 23 over 39 is 10.03. Okay, so for the spot where the 10 is, you take that row, that column, total, divide by that. Okay, so then you got your expected contingency table. And now we notice it's a 2 by 2, so we have to do the Yates continuity correction. And we use this fancy formula. Now, if you notice, this is just the difference between your observed, your expected, that's right here, over your expected. Okay, so as you can see, that's right here. And then each one, you do it for each spot in your table and add it all up. And there's your chi-squared. All right, so knowing your degrees of freedom is super important, okay? However, we can't do what we did before, okay, when we are estimating parameters. So if we're checking whether the distribution is normal, we need to subtract 2 from the usual degrees of freedom. When we are checking for a binomial distribution, we only subtract 1. In a Poisson distribution, we only subtract 1. Okay, so R is the estimated one of these. It's either 2 or 1. Okay, so it's usually n minus 1, but when you're estimating parameters, you got to take off a little bit more. So, of course, let's do an example. So the first thing we want to do is find the degrees of freedom. Okay, so in this case, we have, all right, remember our formula. So it's n minus 1 minus r. So in this case, we have 6 columns. Okay, so n is 6. We subtract 1, and then r would be 2. We're trying to do a normal distribution, and mean and standard deviation are estimated, so we need to subtract 2. So in this case, it is 3 degrees of freedom. All right, so you're going to want to run a goodness of fit test. So you want to make sure you put the observed and expected into your list. Then go to second vars. Wait, is this it? Nope, I lied. Stat. Oh, I can never remember where everything is. Stat, tests, all the way at the bottom. Goodness of fit. Then list 1, list 2, 3 degrees of freedom. You calculate, notice we get 12.2. All right, so the chi-squared is 12.2, well, approximately. All right, using a calculator. Now, think about what that means. All right, so you have your distribution does something like this, right? Out here at 7.81, that's a 5% level of significance. We're past that. We're down here at 12.2. So if it was significant at 7.81, it's definitely significant at 12.2. So Ramon should reject the assumption that the distribution is normal, okay? Because the odds of getting that observed results is very unlikely. That's what that means. Okay, so let's do another example. Joe wants to be a professional basketball player and collected all these results at the end of a year. Okay, so we need, we want to see if this is consistent with our assumption. So we have to state our hypothesis. So our first one is the number of free throws follow a binomial distribution, all right, with unknown probability of success. All right, the alternative hypothesis doesn't follow a binomial distribution. Okay. All right, then we're going to perform our test. So we're going to worry about getting our mean. Okay, and we're going to, if we divide that by 3, then that's going to get our probability. Of course, 3 being the number of trials. Okay. So this would be it overall, and then this would be for each individual trial. That's our p-value. All right, so we're going to take that and determine our expected probabilities, all right, by using the binomial distribution, so the binomial PDF, okay, with 3 being our number of trials and our this value being our probability. When we do that, we get this is our expected. Okay. So we multiply the expected probability. Oh, I'm sorry, I cut that part off. Expected probability times 365, and that's how many we expect in 1 year. All right, so we want to see if ours follow this binomial distribution. And then, of course, now that we have our observed and our expected, we can run our chi-squared, and our p-value will also show up. So we get 0.986. And since that is much larger than 0.05, we do not reject the null hypothesis. Okay, so it's consistent with the assumption that his attempts are independent of each other and it doesn't change throughout the year. Okay. All right, so that's the end of this section. If you have any questions, please feel free to ask me in class.